Hi, so as Mark just said, I work for Red Hat, and primarily I've been working on the Libvirt project for 5 years or so, but kind of like the last 3 or 4 months I've started getting involved in OpenStack, and kind of say my role is to make the OpenStack driver for Libvirt and KVM and LXC the best part of Nova. So I guess that's a bit about what I'm going to be talking about. Right, here we go. So first of all, I'm going to start off telling you a little bit about Libvirt in case you don't already know what it is. Libvirt started off about 5 years ago or so when we were first looking at Zen, and we wanted an application development API for Zen. We realized there was no real API that could be considered a long-term stable API. We also quickly realized that we wanted an API that was going to not be tied to any one hypervisor technology. So we started off the Libvirt project to provide the foundations of an open source virtualization management API. Some of the things about, some of the key points about Libvirt is that it's agnostic to the underlying hypervisor. It's a fairly simple API to get up and running with. There's no great if you look at something like the SIM virtualization API, it's an enormous object model. You have to do a hell of a lot of work just to do very simple things. Libvirt's aim is to make simple things simple, which is always good. It's portable. Primarily, we run manage hypervisors on Linux, but we've also got support for Windows and OS X and Solaris to varying degrees. And it's LGPL licensed. So, did you have a question?
Just a quick question. Is it still a binary protocol?
Libvirt, I'll get
just talking about portable.
Yeah, I mean, there is Libvirt. Primarily, Libvirt is it talks to the local hypervisor daemon, but there is what we call a remote access API, which uses a binary protocol. And the protocol is based on the XDR specification. So that is portable across operating systems and different hardware platforms. So actually, brings us nicely onto this slide, which is just outlining some of the hypervisors that Libvirt can manage. I list the 4 best supported ones here. First, QEMU has probably got the highest level of development. That supports the QEMU emulator and KVM hardware acceleration. The VMware ESX driver is probably our next best supported one.
Lowercase w, by the way.
Sorry. Supports ESX and GSX and all those kind of things. There's actually a second VMware driver which is targeted at kind of the VMware player, but that's a completely different way to control that. The Zen driver, which is actually the first driver that we have developed in Libvirt, that talks to the traditional open source Zen APIs. That's like ZenD and ZenStore and all those kind of things. That's actually in the process of being kind of obsoleted by a new driver, which talks to the new Zen APIs, which are libxl. And there's also yet another Zen driver, which talks to Zen API, which is the API in the commercial product that Citrix provide. In terms of Linux, the Linux containers are obviously a pretty high-profile component of Linux these days. Still under pretty active development. I wouldn't really want to be deploying LXC in production right now, but people do, I'm told. The test hypervisor is basically just a dummy in-memory stub of all of the Libvirt APIs, so you can write applications that work against Libvirt and test them in an automated fashion without actually having to worry about having a real hypervisor behind the system. And then, as mentioned just a few minutes ago, we've got a generic remote access driver, which allows you to control all the Libvirt APIs from a remote host. I list a few more down the bottom: VirtualBox, OpenVZ, Parallels. Those are all in various stages of usefulness, but the ones listed here are kind of like the best maintained parts of the Libvirt code. So I just want to mention KVM, as that's one of the items in the title of this talk. I expect most people know what KVM is. It's the Linux kernel's native hypervisor providing full virtualization capabilities. So Linux is actually your hypervisor layer. It uses QEMU to provide the device model to the guest, and there's probably QEMU has actually got a much the kernel part of KVM is quite small, and most of the really hairy stuff goes on in the QEMU device models. QEMU emulates all sorts of hardware from all sorts of different architectures, but from the point of view of KVM, the hardware drivers that are interesting are those that are using virt.io. These are para-virtualized device drivers designed to give better performance than emulating some real hardware like an E1000 NIC or whatever. So there's virt.io drivers for disk and network primarily. There's a virt.io balloon driver for doing memory adjustments on the fly. There's something called virt.io serial, which basically gives you a para-virtualized serial port, or lots of them in fact. So you can run application protocols over that. For example, the virt.io serial is what QEMU uses for its guest agent protocol. There's a virt.io RNG for providing random entropy to your guests. So actually getting good random entropy in guests is often quite a problem. So that's just a quick overview of what KVM is. I'm not going to go into too much detail about it, so I hope most people know what KVM is. More interesting from my point of view is what benefits Libvirt brings to KVM. Obviously, KVM and QEMU are standalone projects. You can use them directly. You can talk to their various protocols, and you can launch them with arbitrary command lines. But I like to think that Libvirt offers a bunch of benefits over talking to KVM directly. One of the first ones is that we do validation of the CPU model exposed to the guests on migration. So if you have a virtual machine running here, you migrate it to this host over here. The two hosts might have different CPUs. You want to make sure the guest's view of the CPU doesn't change. So that's one of the things Libvirt does, is to validate that and enforce it. Following a similar vein, you also want to make sure the hardware model in general that you expose to the guest doesn't change. So if you start a guest here, you hot plug some PCI devices, you hot unplug some other PCI devices, then you migrate it. You want to make sure that when the guest starts up on this host over here, all the PCI slots will still have the same numbers, as guests will tend to get unhappy if those change behind their back. So Libvirt deals with stable device addressing and ensures that is maintained across migration. The QEMU provides some support for migration, but it does this just using plain TCP sockets. So if you don't trust the network that's running between your two hosts, you probably want to have some kind of secure migration channel. So Libvirt provides the ability to run the migration traffic over a secure socket, typically secured with TLS, or you can use SASL and Kerberos, which also provides an encryption capability. Two key benefits of using Libvirt instead of talking to KVM directly is that you'll always be following the best practice for launching KVM, and well, QEMU in particular. If you follow the QEMU development for any length of time, you'll notice they're constantly rewriting things and changing the way you do things, and it's pretty hard to keep up with what their best practice is. And that's, in terms of the ongoing Libvirt maintenance, we talk to the QEMU developers quite actively to find out what their recommendations are at any time and try to update our code to support those. So Libvirt kind of ensures you're always following the best practice for using KVM and QEMU. The last point, if you've got very large guests and you want to save the state of the guest to disk, you can find you get very big save files on disk. So it's nice to be able to compress those. QEMU doesn't have any built-in ability to compress the save image it creates, so Libvirt adds that capability. We also make it use ODirect, which bypasses the kernel caches, so you don't fill up the kernel I/O cache with stuff that you just want to go straight to disk. So that's quite a good performance win, actually, particularly under high load to use ODirect. In terms of resource controls, QEMU has some very basic resource control capabilities built into it, but in general, kind of Linux is going towards using C groups for resource controls. So Libvirt has done quite a lot of work to integrate C groups and KVM, so that every guest you start up gets put into a dedicated C group, and then you can apply controls to the CPU usage, memory usage, disk I/O, network I/O, and that kind of allows you to set up policies for fairness between all your virtual machines. To be honest, I mean, we've done a lot of this functionality, but I don't know how much people are actually using this functionality yet. Everyone wants resource controls, but very few people can tell me exactly what they want to control with it. They just know they want to control stuff. It can be quite frustrating. Obviously, when you're dealing with migration and virtual machines across lots of hosts and shared storage, you want to make sure you don't start the same. You want to make sure you don't start two virtual machines pointing at the same storage at the same time, because if you haven't got a cluster file system, you're probably going to trash all of your data. So Libvirt includes a disk lease management facility, which allows it to take out exclusive leases on any disks that a VM is using, and that offers protection against concurrent usage. So that can be quite an important factor. QEMU doesn't have anything like that built into it, so Libvirt has to add that on top. Encryption is another interesting one. QEMU actually exposes the ability to encrypt QCal disk images. And you might wonder why this is useful. Well, if you've got a different team of admins working on your storage versus your virtualization hosts, you might trust your virtualization host admins. In fact, you have to, because there's nothing in a virtualization host that stops a host admin doing anything with VMs that are running there. But you might not trust your storage administrators. So if you use QCal disk encryption, it means the storage administrators can't get any access to any data that's stored in disk images. Only administrators who have access to the virtualization hosts themselves can get access to the disk images. So that can be useful for some kind of deployments. Security is one of the things, one of the most important factors when dealing with virtualization, because in the pre-virtualized world, you obviously had physical barriers between your different operating systems. Now you're running lots of operating systems on one host. You want to maintain those barriers as best you can. Obviously, as a first level, you can run the QEMU instances as separate user IDs, but you really want to do better than that. So one of the big things we've done with Libvirt is to integrate support for mandatory access control. We typically refer to this functionality as SVirt. It originally was written to use SE Linux for isolating each virtual machine, but has since been ported to use AppArmor as well. And that's the SE Linux stuff is enabled out of the box on any Fedora or RHEL system. The AppArmor support is enabled out of the box on any Ubuntu or Debian system. So you've got strong mandatory access control applying, which isolates each individual QEMU instance. So if for some reason there's a flaw in QEMU and the guest OS manages to compromise QEMU, it's still confined, so it can only access the resources which were assigned to that one VM. That's pretty important. Capabilities. This is kind of a low-level kernel feature which most people don't know about or care about, but basically what it boils down to is we set up the Linux capabilities so that the QEMU processors have no ability to run setuid programs. So even if there was a failure in SE Linux and a failure in QEMU, and they tried to somehow launch a setuid program to gain privileges, they wouldn't be able to do that. The C groups are typically thought of as a resource control mechanism, but it also has a simple security mechanism for controlling device access. You can set up whitelists of which block devices and which character devices you want to process to use. So we enable that by default for all QEMU virtual machines, so that you can only access block devices that were explicitly assigned to that virtual machine. That's just another layer of protection in all the things that are done there. And the last point a lot of people don't care, but if you start talking to government organizations, they like their security standards. So KVM on RHEL has also got common criteria certification. So that was the first half of my talk, a bit about Libvirt and KVM and QEMU. Now I want to talk a little bit about OpenStack Nova, since that's what most people are here to listen about. So as you heard in the previous talk, Nova is the part of OpenStack which provides the compute service or compute fabric. It runs your virtualization hosts, basically, and provides the APIs for managing them, whether via the native OpenStack API or the EC2 compatible API. You have your choice, both are there out of the box. Nova itself has a concept of a hypervisor abstraction layer, so Nova supports different hypervisors. It supports VMware, supports Zen by the Zen API. It supports Libvirt. Libvirt, of course, in turn supports many other hypervisors. So you've got a choice in the ways you deploy OpenStack and choose your hypervisors. Most of the Nova communication internally takes place over a reliable message bus. You've got a choice of message bus implementations here, AMQP, RabbitMQ. I think there was one added for 0MQ. AMQP is
RabbitMQ is AMQP.
Oh, sorry. No, I should say RabbitMQ and Cupid. They both implement different versions of the AMQP specification. So unfortunately, they're not compatible. But hopefully that'll be resolved in yet another iteration of the AMQP specification. And of course, as you heard before, Nova integrates with Quantum, Cinder, Keystone, and Swift, and other ones that I've probably forgotten. The Nova Libvirt driver is what I spend most of my time working on. This driver uses the Libvirt hypervisor APIs primarily. The Libvirt API actually does a lot more than just managing hypervisors. Libvirt can manage storage, it can manage networking, it can do host network configuration, it can do host device pass-through and all sorts of things like that. But Nova, as it stands today, only really uses the hypervisor part of the Libvirt API. And it talks to that using the Libvirt Python binding, and just talks to the local Libvirt daemon instance. In that, although Libvirt supports quite a wide range of hypervisors, as I mentioned a few slides earlier, in the context of Nova, there's only really 4 hypervisors that we currently are set up to use. The Zen driver, the QEMU driver, which also supports KVM, the LXC driver, and the user mode Linux driver, although I'm surprised if anyone really uses the user mode Linux driver these days. In terms of configuring the virtual machines, again, it's fairly simplistic in what it configures. It's mostly focused on configuring storage for the virtual machines in a variety of different ways. And it also has some basic support for configuring networking, typically based around a Linux bridge device or more recently Open vSwitch. And as well as those, it does network traffic filtering. So this is mostly to prevent one virtual machine spoofing traffic from another virtual machine, so it'll do MAC address filtering, so a VM can only send packets with the MAC address that it was actually assigned. Same, it'll do IP layer filtering so that you can't spoof another VM's IP address. And it has two ways of doing the filtering. It can either use Libvirt's network filtering capability, or it can use IP tables and EB tables directly. Depending on what hypervisor you choose to use, the virtual machines will be booted in a different way. If you're using user mode Linux, it just boots user bin Linux and gives you the disk that you configured for your instance. If you're using LXC, then it will take the image that you provided, and it will mount it loop back as the root file system, then it will just run the sbin init program that's in that file system image. If you're using Zen, QEMU, or KVM, then you've got a choice of methods to boot. You can either provide a kernel and an initRD, and it will boot those directly, or it can boot the disk images as if it was a hard disk. That will do a regular BIOS boot using grub, or it can just boot it as an ISO image. Disk configuration, as I mentioned, is quite flexible. You've got, well, I mentioned LXC has loopback devices. KVM, Zen, and UML have a wide range of disk devices. You've got a primary disk. You've got an optional config disk, which provides metadata for the guest virtual machine instance. You've got an optional swap disk, and you can then also add any number of other ephemeral disks. Ephemeral disks are disks that exist for the time that the VM is running, then are thrown away when it shuts down. So if you want any kind of persistent data for your virtual machines, then you have to set up persistent volumes. Most of those you can have a choice of raw or QCal. The persistent volumes are all raw at this time. So a few things that are new in the fulsome release, which is the one that's coming up. These are mostly things I've been working on, but there's been some other contributors to some of them. One of the first things I did was to get rid of the template-based configuration of virtual machines, because that was really complicating the code by splitting the configuration across 3 different areas of the code base. To replace that with a formal configuration API that's internal to the Libvirt driver. Following on from that, we were then able to set up KVM instances, so they used optimized timers. Just make sure this was basically about making sure you don't get clock drift when your virtual machines are running. That's quite an important thing for KVM. Allowing the CPU model to be configured is an important performance point. Historically, OpenStack has just launched instances using the default CPU model, which is generally not going to take advantage of your hardware's full capabilities. So in Fulsome, it will now default to using the host CPU model, so you get full advantage of all of the capabilities that are on your expensive, shiny new CPUs. So that's good for performance. For flexibility of deployment, you can now set it up to use LVM volumes for the ephemeral disks instead of just using a raw file or a QCal file. From a maintainability point of view, you can now query for diagnostic information about virtual machines. This tells you disk I/O rates, network I/O rates, CPU utilization, memory utilization. Another maintainability thing is to stop using /temp for multi-gigabyte snapshot files. And from a flexibility point of view, work in progress is to add support for running Zen full virtualization. So currently the Zen code only runs paravirtualized guests. So this should all be in the new fulsome release. Looking forward to the Grizzly release, which is the next one, shortly going into planning. One of the things is to make the configuration of virtual machines more flexible, so that we can have optimized hardware setup for lots of different operating systems. So Linux may use VirtIO. You can get VirtIO drivers for Windows, but if you want to run BSD or something like that in your cloud, you're not necessarily going to have VirtIO. So we want to use a library called libosinfo to figure out what the optimal hardware configuration is for running instances. And also identify what type of OS is in an ISO image. So again, we can optimize the deployment of that. From a security point of view, I want to integrate the support for QCOW encryption so that all the cloud disk images can only be accessible by administrators of the virtualization hosts. You no longer have to trust the storage administrators. From a maintainability point of view, we want to add support for watchdogs so that if the guest OS hangs, we can identify that and take appropriate action, or at least tell the user what's happened so they can take appropriate action. From a performance point of view, if you go to benchmark KVM on large NUMA machines, you'll find that you really need to do intelligent NUMA placement to get the best out of your hardware. And I mean, really want to do good NUMA placement. You can see 30 to 40% improvements by doing the right NUMA placement on some workloads.
Does everybody understand what NUMA is?
Sorry, possibly not. In the traditional PC world, all memory and CPUs are in a kind of symmetric model, so any CPU can access the memory and have the same latency. But in a NUMA architecture, they split the CPUs and memory into different regions. So for one CPU can access this region of memory locally, and this other region is further away. So you have differing latencies to different regions of memory. So if you place a VM and you set it to run on these two CPUs, and they're on different regions or NUMA nodes, then you can get very bad performance because you're increasing the latency to access memory. So making sure your VMs run entirely within one NUMA node and have all their memory within that NUMA node is pretty critically important for getting good performance. And this problem is only going to get worse as the hardware in the x86 world gets bigger. And we want to do a bit of work on improving the resource isolation of virtual machines. That's using the C groups functionality. So I see I'm getting dirty looks to finish. Fortunately, that is
the food being served. So
fortunately, that is the last slide. So that's all.
It was okay with everyone. I think we can take questions offline.
Yeah, sure. Just come up to me and ask me questions whenever.
So, just in the interest of